Welcome to this lecture of microscale transport process. What we have been discussing is immiscible flow through microchannel. We have introduced Laplace pressure and we have introduced certain stability criteria when you have two phases present together. I mean, when they split into, when they break into droplets or bubbles, that we have briefly touched upon. What I will do in today's class first what I will do is I will introduce some dimensionless numbers. These dimensionless numbers are extremely important in this context, and then I will try to find out how we can calculate the pressure drop through a microchannel when we have this immiscible flow happening. Okay, what would be the pressure drop and what would be the size of the bubble, or what would be the size of that annular outer liquid. So, these issues we will address in today's class. So, first let me introduce some dimensionless numbers which are very important in this context. What we will be talking about here is something called bond number, capillary number, Weber number, and this is the fourth one. Okay, bond number. Let me just give the desk first with symbols. Let me put it how bond number looks, and then we will try to find out what is the significance of this. Rho is the density, g is the gravity. Of course, you can say density of which phase. So, this is probably density of the discrete phase. Okay. So, let us and let me point out that there is another version of capillary number. This is not the end of this capillary number. There is another version of capillary number. In fact, the alternative definition of capillary number would be mu v d divided by 4 sigma L. This is another definition. This is a different definition. This is not a product. This is one definition, or this can be another definition. Here you can see these are dimensionless numbers. Here also it is dimensionless. You have multiplied it by d by 4 L. Okay, d by 4 and L, d by 4 divided by L. So, that is what you multiplied this with. Here d is the diameter of the droplet and L is the so one is the characteristic dimension of the droplet and other is the characteristic dimension of the channel. So, this is an alternative definition which could be useful. Okay. Now, let us focus one by one on what we have, what do they mean. Bond number basically compares gravitational force acting on the fluid with compare something with something, right. So, with interfacial force. The way this is conceptualized is that the gravitational force, these would be dimensionally, it would be rho g L cube. This would be rho g L cube. How is it so? We know that for gravity, for a hydrostatic head, the pressure, the delta P is written as rho g into L. That is how delta P is written, H rho g, right. So, delta P is rho g L. So, this is the so rho g L signifies the pressure. So, now if you multiply this with L square, that means the area. So, then only you get a force, right. So, if you want to call it gravitational force, then it will be rho g L into L square, that is what we have written here. Whereas, in the interfacial force, what do we have? Interfacial force is I mean, how is interfacial force written? It is written as sigma into L, right. You all know Newton per meter. In surface tension, the unit of surface tension is Newton per meter, and that has to be multiplied by the meter. So, you get a Newton. So, you get it in Newton. So, you got to multiply by the L dimension L, then only you get the force, and here you got to this represents the gravitational force. So, the ratio of these two, that means rho g L cube divided by sigma L, or in other words rho g L square divided by sigma. So, that is exactly what is bond number. Okay. So, what does this mean? This means that when bond number is, of course, I mean you got to understand here is that rho is the density of discrete phase. Discrete phase means you are producing oil droplets in water, or you are producing bubbles in water. Then the discrete phase here is air and the continuous phase is water. Discrete phase is the droplet or the bubble, that phase is discrete phase. So, rho represents that density. So, what this means is a very large bond number implies gravity dominates over interfacial force. Okay. So, very large bond number means a flat puddle of liquid, a flat puddle of liquid. You understand what that means, a flat puddle of liquid. Okay. On the other hand, I mean, let me point out what happens if one number is very small, then you will understand what this puddle of liquid means. Very small bond number, this implies almost droplet, spherical droplet or bubble. Okay. So, by looking at the bond number, if the bond number is large, you can expect that it will be a puddle of liquid. It will not form a sphere, it will not form a droplet, it will not take a spherical shape. Okay. On the other hand, if the bond number is very small, invariably you know that there would be this there would be the shape of this discrete phase would be spherical, because interfacial force will dominate over the gravity force. Okay. Now, the problem would be if bond number is, if the bond number is close to 1, then it needs detailed calculation to find the shape. You cannot predict the shape. Also, in your calculation, if you want to ignore gravity, then probably one justification of doing that would be that you are working with a small bond number. Okay. So, these are the few things you can have. Now, let us get a feel for what could be a bond number in case of a microchannel. If we look at say 100 micrometer droplet of water in oil, water density you assumed is 1000 kg per meter cube and oil density you assume as 800 kg per meter cube. Okay. This, and if you assume the sigma to be equal to, sigma is of the order of, say, what is the sigma we mentioned in the last class? Or okay, water and oil we have not mentioned anything. If we assume close to, say, 10 millinewton per meter, I mean if it is of the order of 10 millinewton per meter, what would be the bond number in that case? I think bond number would be of the order of 10 to the power minus 3. So, you can conclude that the droplet will be spherical. All right. So, these are the some of the numbers that you can work with. The next dimensionless number we had defined here is capillary number, which we said is mu v by sigma, and an alternative definition would be mu v d by 4 sigma L. Now, here we have we do not have rho, here we had rho, and we said rho is the density of the discrete phase. Here we have mu. Okay, let us first point out what capillary number means, because you have to mention whenever such thing happens, we have to mention that mu of which phase, because we are working with two phases. So, here think of it this way, that tau dimensionally, tau is what? Tau is mu du dy, you call it. Now, du dy, if at the wall it is 0 and if a distance L away from the wall it is v. So, you can call this mu v by L. Okay. So, that is the shear stress. Okay. And the interfacial stress, I mean if we look at the interfacial force is equal to sigma into L. You understand, Newton per meter into meter cancels out, so it is Newton interfacial force. So, if somebody wants to find out what is interfacial stress, he will write this sigma L divided by L square, force per unit area. So, this becomes equal to sigma by L. So, if somebody wants to find out the ratio of viscous stress, if somebody wants to compare, say, compare viscous stress with interfacial stress, then this would be equal to mu v by L divided by sigma by L. L cancels out, and so invariably you end up with mu v by sigma. So, that is basically the definition of capillary number. That is basically the definition of capillary number. Now, here we have already mentioned that there is an alternative definition. The alternative definition, the meaning of alternative definition would be that you are working with the alternative, let us write this as alternative capillary number, that is equal to you continue with the shear stress term, the tau, and you here you write this as sigma into pi d divided by pi d square by 4. What do we do here? On the top, we instead of tau we can write this as mu, instead of tau you can write this as mu v by L. That is what we have done earlier here, that tau is equal to mu v by L. Tau is equal to mu v by L. However, here the interfacial stress is written as sigma by L square. So, what did we do here which we are not doing here? You understand that, right? Here we are keeping the dimension L that is used for viscous stress and the dimension L that is used to calculate interfacial stress as same. But for a droplet or a bubble flowing through a microchannel, the dimension of the droplet and dimension of the channel, these two length scales, the characteristic length scales would be different. So, what you are doing here is you are continuing here with mu v by L, all right. But here instead of sigma by L, what you are writing is sigma into pi d divided by pi d square by 4. That means, so this is how we are defining the interfacial stress. So, what you would get in this case is mu v by L divided by 4 sigma by d. Is there any other way you can get this 4 sigma by d? I think this is what is the interpretation of 4 sigma by d. Think about it. Now, the channel. So, here what you are doing is here the channel dimension L and droplet dimension d are separated. So, this implies provision for two different characteristic length scale. One for the shear rate and other for the Laplace pressure. Okay, so this is an alternative definition. Now, there are a couple of things you need to appreciate here with regard to capillary number. So, before we proceed to the next dimensionless number, we must point this out, is that in shear flow, large droplets are elongated. I mean, it is understandable. I mean, shear we have already talked about these elongational, what we call it, linear stretching and all kinds of things. So, basically you are stretching the fluid. So, if instead of the fluid there is a droplet, so droplet will also be stretched. So, large droplets are elongated, and so when large droplets are elongated, that means that they will undergo relief plateau instability that we have talked about, right, in the last class. That this will, moment you stretch this, moment you have a droplet, moment you have an immiscible cylinder, moment you have a cylinder, that cylinder will break into smaller droplets because of certain instability. Now, so that instability will come into play there. Now, if you have this happening, so that means I can say the large droplet will be fragmented will be fragmented into smaller ones till what time? It will be fragmented, but fragmented to what length scale? So, it will be into smaller ones until, this is important, until the radius is small enough that the curvature with associated Laplace pressure balances the shear stress. What that means is essentially the capillary number is equal to 1. So, until the radius is small enough that associated Laplace pressure balances the shear stress. Okay. And this happens when capillary number is equal to 1. Okay. So, if somebody wants to find out what would be that limiting radius that this droplet will achieve, I mean I have put two phases together and I am having those two phases flowing through a tube, flowing through a small tube. I would like to know what would be that limiting radius to which these droplets would be fragmented. That radius can be obtained by equating capillary number is equal to 1. So, that means the radius of the droplet can be, so what we mean here is that the radius of the droplet can be approximated by setting capillary number is equal to 1, and capillary number is equal to 1 in, if you look at this, if this is the alternative capillary number, definition of alternative capillary number, and if this is equal to 1, that means you get some idea of what is D. What is D? D would be close to 4 L sigma divided by mu u or mu v. All right. So, that would be the diameter of the droplet. So, this would be the diameter of the droplet. You can expect this is the limiting diameter of the droplet. Okay. Another issue is that you can check the capillary number and whether the capillary number is greater than 1. If you have a higher capillary, so in a particular flow, when you have a flow through a microchannel or flow through a channel, let us put it, and you calculate the capillary number, and if you see that the capillary number is greater than 1 or capillary number is high, in that case you can conclude that the shear can dominate in this fragmentation process. On the other hand, if you have a flow through a channel where you see that the capillary number is low, capillary number is not significant, capillary number is less than 1. So, in that case you would be you can conclude that you cannot expect much of a breakup arising from the shear flow. By imposing shear, you cannot break it into you cannot get into this fragmentation. So, this capillary number is an indication how effective shear will be to break the droplets. So, if you get a good microchannel, if you see that okay, your capillary number is pretty high there. So, you know one thing for sure, that if you introduce the if you know that you have some shear environment in which you can introduce these immiscible phases and you can elongate it, then you know that you will be able to fragment it. But the capillary number would determine whether you will be able to fragment it or not, and you can see what is the limiting value of diameter that you can expect. Now, let us go to the next dimensionless number, which we called Weber number. Weber number, first of all, this compares the Weber number, this compares inertial stress with interfacial stress. Inertial stress, this may arise in case of a jet, a elongated jet that breaks down. Okay, it is not a viscous stress, it is inertial stress. So, that is how it is different from capillary number. So, if somebody is observing a jet and the jet breaking down, so that is probably the case where you have this Weber number. Let us see how we get into this. Weber number is there can be two interpretations possible. First of all, Weber number is rho, we said that rho v squared L divided by sigma, that is the form. There are two interpretations possible. One is that it is written as kinetic energy which is given by rho v square, that is per. So, rho v square is typically per unit volume. So, this multiplied by L cube. So, that is the kinetic energy, this divided by Laplace pressure, which is basically not exactly the Laplace pressure. The way we interpret this is, it is sigma divided by L into L cube. So, how do we look at it? Sigma by L is basically the pressure, this multiplied by L cube. So, are we talking about the energy associated with Laplace pressure? Probably something, yeah, that is what you are looking at. Or the other interpretation could be that you think of it as rho L cube. This gives you the mass, and then you have v square divided by L. This gives you the acceleration divided by sigma into L. So, this is an interpretation of inertial force divided by interfacial force. So, this is one interpretation you can think of. This also leads to rho v square L by sigma, or you can write this as energy corresponding to this quantity. So, this is also another interpretation possible. Okay. Anyway, the large Weber number, implies elongated jet that breaks up into droplets far away from the nozzle. Right. Now, if it is a small Weber number, This implies interfacial tension effects will lead to dripping of droplets without formation of pronounced jet. So, large Weber number means elongated jet that breaks up into droplets far away from the nozzle, and small Weber number means interfacial tension effects will lead to dripping of droplets without formation of pronounced jets. Do you understand what we are talking about? Suppose, I mean, it will think of it this way, that I have a pool of some phase, okay, and you are introducing say another phase. It could be that you are introducing air into a pool of water. It could be that you are introducing water in a pool of oil. I mean, it could be one phase you are introducing into the another phase. So, that would be in the form of some tube would be inserted into that reservoir, right, into that pool, and then you are forming, you are calling it droplets, bubbles, because you know that moment you are introducing a cylindrical, you are introducing a cylinder, right. That is, if you have a flow, you are introducing a cylinder. If there would have been no other obstruction, the flow should have continued like a cylinder, but due to instability, this cylinder will not, it cannot continue that way. Instead, this cylinder breaks down. Now, where it breaks, whether it breaks immediately next to the nozzle, where it enters, where the nozzle enters into the pool, or whether it will whether it will drip from the nozzle, or it will go and break far away from the nozzle, that effect can be found out from this dimensionless number. Probably here I am just briefly touching these I am just mentioning or I am trying to give briefly the significance of these dimensionless numbers. When you are actually working with it, probably the people who are really working on these dimensionless numbers, they probably have better interpretation of it, but for that you need to play with this number for long. I mean, you have to do theoretical study with these numbers, then probably you can have that kind of handle. Here I just touch upon the significance of these numbers in nutshell. The next number that I have here, or the last one in this lot, is this number. Here we mentioned that this number the expression is mu divided by rho sigma L to the power half, and this number compares viscous and inertial forces in the motion of interface between two fluids. I have not I mean, so far the work that I have done, I have not used this number. If any of you have done that, probably you can share your thoughts about these numbers. Basically, I just mentioned here that this number is there, and there is a basically these dimensionless numbers. I mean, if you come up with a system where you think that there would be a dimensionless number would be appropriate, you can create your own. I mean, basically, see, introducing dimensionless number helps you in expressing the results, helps you in analyzing the results. So, I mean, it's a very open forum. I mean, the researchers have studied several systems and they have introduced those numbers. In fact, if you go to internet these days, you can see earlier it used to be in the back side of the book, the entire list of dimensionless numbers that are already people have which are recognized dimensionless numbers. Now, the system that you are working with, you can find some dimensionless number, will help you analyzing the results, and that you are free to use that number. The point is that if people find that the systems other people are doing, other people are researching, and they continue to I mean the research they are doing, they need that same dimensionless number in various places. So, then probably this dimensionless number will be important, and the person who had floated, who had put forward this number, he would be recognized. So, that is the whole idea. So, it is a very open forum, and keep an open mind when you are studying a system, you see what dimensionless number should be appropriate. In fact, it would be a very it would be a puzzle, it would be a creative work if you can come up with the right definition of the system through these numbers. That is what we had as far as these dimensionless numbers are concerned. So, what I will do next is I will get into the first I before I get into the pressure drop calculation, let me point out couple of details of bubble in a, let us say, micro channel. Now, one thing the analysis that I am going to present here, one thing I would like to point at the very outset is that the contact line resistance is not present here. Contact line resistance is not present. That means one phase completely wets the surface. The other point, I mean, I would like to work with some of the I would like to play with the numbers to see what would be the importance of Laplace pressure and the pressure drop for a flow through a pipe. Okay, pressure drop for flow through a pipe. What was that, Hagen-Poiseuille's equation, or what you have? If you take that pressure drop, and if you compare it with a Laplace pressure for that same channel, I mean for the similar dimensions, I mean how these numbers look, that let me point out here. If I write the pressure drop necessary to drive a liquid slug of length L, I am not talking about two phase, I am talking about one phase, liquid slug of length L, let us say small l, at speed say capital U in a channel of radius. We are not we are talking about a circular channel, circular cross section, channel of radius r. You will find that this pressure drop is of the order of U L mu divided by r square. Okay. Now, if we consider the for a stagnant bubble, that has that radius of curvature of r. So, with radius of curvature is equal to R. So, for a stagnant bubble, the capillary pressure drop across the bubble cap is 2 sigma by R, that you already know. Now, if we set these two pressure drops, I mean if we try to find out how these, what should be these L, for example, or in other words, what I am trying to do is I am trying to find out if somebody, if some length of slug provides a pressure drop which is equal to this pressure drop. If you try to find out what would be that length of the slug, length of the liquid slug, that can for driving that length of the slug you need a pressure drop, and you are trying to equate that pressure drop. So, you want to get a feel for what would be the length equivalent, liquid slug length equivalent of these Laplace pressure. Okay, if you want to do that, you will find that L divided by R, that is equal to 1 divided by mu u divided by sigma. In fact, you are getting another interpretation of capillary number, don't you? I mean, L divided by R is equal to 1 by mu u by sigma. This you are talking, this we said is the capillary number. So, this is another interpretation of capillary number, that capillary number gives you comparison here. If you had what would be the length of the liquid slug that you can drive with the same pressure as the capillary pressure for that stagnant bubble. So, this is the value. Now, if somebody finds out, say for the velocity range, let us talk about a range, say u, range of u is say 1 micrometer per second to 1 millimeter per second. Let us put this as the range for u. You will find that if you take water and air and their corresponding interfacial tension and everything, you will find that the capillary number would be equal to 10 to the power minus 7 to 10 to the power minus 4, corresponding to this range of u, 10 to the power minus 7 to 10 to the power minus 4. So, can you imagine what would be the case in this case? Now, L divided by R is equal to what we are saying is 10 to the power 7 to 10 to the power 4. That is what we are saying. So, can you imagine what would be the length of the slug we are looking at? Length of that liquid slug, which is equivalent to the Laplace pressure corresponding to or the capillary pressure corresponding to that bubble, that is of this order. I mean, what this means is L is much higher than R. So, this basically shows the level of pressure required to insert the meniscus in the capillary. So, the problem here, I mean, when it comes to having this two phase flow, the problem here is the problem lies in accommodating large radius of curvature of the interface between two phases in a small channel. All right. Now, the calculation that I showed is not I mean what we are interested in at this point is probably the for a flow of bubble. That means, what we are interested in here is that if you have a, if this is the wall, and if you have train of bubbles, this is one bubble, this is another bubble, then there will be another one like this. So, you have a train of bubble flowing. Okay. So, for the pressure drop for the flow of this train of bubbles, that is again somewhat different. The mechanism would be somewhat different, because we need to understand how these annular region will behave. That is also important, how this part will behave. So, that needs to be understood. So, that and in fact the pressure drop calculation for the flow of a train of bubbles, that should come from that understanding of how these annular region behaves. So, that has not been accounted. So, what I mentioned here is probably the what you call back of the envelope calculations. So, this is not actually the rigorous one. What we are interested in is this, but I would like to point out, I mean, if somebody compares the Laplace pressure and the pressure drop, the conventional pressure drop of a single phase, and particularly in the context of flow in a microchannel, what they will end up with is these numbers. That is what I am just trying to emphasize. Now, here I mean what I will be taking up next is how to address this. Bubbles are moving at a velocity u, and in this annular region here, of course, at the wall the velocity has to be 0, and then there would be a velocity profile from here to here. Mind it that these dimensions are small. So, there are certain existing theories. I mean, nobody is inventing new things here. Already there has been a good amount of work done in the area of lubrication. So, that some of those theories will be invoked to understand this annular part. Okay, this annular part, how these theories of lubrication can be I mean, we will look into that, how that can be invoked here. Now, there are certain considerations we need to have here. One is that bubbles are already placed. I mean, when you get into this pressure drop calculation, your frame of reference is that bubbles are already placed axisymmetrically within the channel. What does axisymmetrically means is that if this is the axis, then this bubble is axisymmetrically placed. That means, it is not that one bubble is sitting in one corner and then the annular region is it is a perfectly perfectly I would say two circles, they are forming the annular region, and inside this is the bubble. Okay, so this is axisymmetrically, these bubbles are axisymmetrically placed. The other assumption that you have is weighting annular film is formed around the bubble. A weighting annular film is formed around a bubble, and this is that annular film we are talking about. and this is weighting the wall of the microchannel. So, this is what you are assuming, and you are assuming that a bubble is moving at a velocity u. Now, what we will do at this point, I mean for probably in the next class, what we will do is we will focus on this region. We will focus on this region. We will come up with a velocity profile for the liquid layer, considering that this wall is moving. So, using this theory of lubrication, we will be finding out a velocity profile within this layer, and that is going to affect significantly the final derivation of pressure drop, because what we are interested in is the pressure drop to have these train of bubbles flowing through this. Now, if you look at these bubbles, what we have to find, what you see here is that there is a curvature, right. I mean this is uniform, this is symmetric. Now, here it looks like a cap. So, this we will call a front cap, and this we will call the back cap, because bubble is moving in this direction. And as a matter of fact, these front cap and back cap, they cannot be symmetric, because they have to be asymmetric, otherwise the bubble will not flow. That is one condition you have. And then you have this part, this thickness, we will call this as h infinity, and then we will be considering h at various points. So, we will be considering h as a function of x. Okay. And finally, the profile that you have, that has to match with the cap part. Okay. Now, there are a lot of other issues involved. In fact, the bubble here, you will find that the force arising from surface tension, that is not uniform everywhere. Some places it is more, and some places it is less, and that will be causing the surfactants to be loaded in one place, and surfactant, the absence of surfactant in other places. So, there would be some imbalances coming up there. So, it is a complex, I mean if you get into the complexity, of course, there will be complexity. If somebody wants to treat this as a black box, okay, I just find out delta P empirically with the voidage and with the flow rate, I can do that. And if you want to get into the complexity, there are several such complexities possible. I will try to address them as far as possible, and my final aim is to come up with a delta P, that is delta P in terms of probably capillary number, probably in terms of things which, for example, if I say it is in terms of h, then you will ask me how will I measure h. Okay. In the microchannel, I cannot measure the dimension even. So, how do you expect me to measure that? So, I will not do that, but come up with an expression. That is the job of the researchers, is to simplify the complex world. So, we will continue this lecture in the next class. That is all I have for today.